Hello and welcome to this lecture on our DAG node setup. This will be quite an in-depth lecture, and it's going to go into a lot of detail. There's quite a lot of code, about 200 or 300 lines within our DAG node, and then another 100 or so within separate modules. But it's going to give us a huge amount of power, essentially, within our DAG structure, and it's going to make accessing my functionality through Python very quick and easy. It essentially gives us another inherited class, or class which is inheriting our dep node, that gives us more and more functionality that we can then pass down the chain into our joint nodes, into our mesh nodes, or any sequential nodes that you would like to make after this. This will be one of the bigger lectures, along with the next one, which will be even bigger, making the attribute setup. So stick with me, and we'll start busting through this right now. The first thing that we need to do is to create our file. So let's go into base, new, Python file, and let's create a DAG node. With the same naming convention, an underscore between the DAG and the node, all lowercase, and then a Python file, and hit enter. Brilliant. Okay, awesome. Now, next step, we're going to go back to our dep node. I'm going to copy out everything that we see here. Yeah, let's just copy out the whole first part of the structure. And we'll just rewrite everything as we go. Okay, brilliant. So what we've done there is we've copied all of our code over, and what we've done is we've just renamed the docstring as needed. So this can deal with items or items with or without dependency. It doesn't really matter. Generally, the whole point of this structure, as we talked about in our introduction, is that it gives us a bit more of a clearer way to access items with or without. So I would generally say that this one should be dealing with nodes with dependency. And then we've renamed our class, calling it DAG node, and started going through the docstring. Now, essentially what we're passing this is the same, because what we're going to do is we're going to inherit our dep node. Okay, so you see what we've done here is we've imported our dep node, and we have inherited that into our DAG node. So now all of the functionality that we saw and we just created, a string, repr, equal, node, setter, getter, properties, path, is reference, exists, all of this functionality is going to be passed straight through to our DAG node. So every bit of functionality that we add within here will make our node more powerful and give us a lot more functionality. But the first thing we need to do is we need to make sure that we are copying the initiate, and we are just stealing everything that we need. Now, one thing we do need to do is we need to make sure that we have DAG initiated with none before. And then what we are going to do here is we are going to go dep node. We're going to go dot dunder method initiate, and then we are going to pass self and node. So this will now initiate our class straight after we have already initiated our DAG within our class, because we'll talk about this a little bit later on, but we need this DAG to be initiated first before our dep node overwrites that functionality or overwrites that variable. So we're doing exactly the same thing again. When we create, we are essentially going to make sure that we create our node if it exists. Or if it doesn't exist, sorry. So if we don't have anything there, then we'll just go ahead and create it. Okay, perfect. But what we do want to do, we want to actually, let's do one thing quickly. Let's do a little bit of housekeeping. We want to make sure that we have this great import that we have up here. So let's go through to our init, which is located within our nodal folder structure within the init. And then let's just copy this line. So within base, we're now going to change that to the DAG node. And again, change the E and the P for an A and a G. And that will save us in the future when we're having to import things, so that we can just import everything in much the same way as we do with the dep node, where we just go modules, nodal, dep node. We can now go modules, nodal, and DAG node. Brilliant. Okay, so let's move on, and now let's start putting our setup together. Let's create our node getter and setter. So let's copy over from dep node actually, and get this divider, just so that again we can keep this kind of similar setup going. Okay. Actually, one thing I'm just thinking, let's have a quick look in our dep node. So in our dep node, we're actually doing the same check here. We are checking that we're not actually existing. So if a user tries to create this node and it already exists, it won't go there. But we also have the same check within create. So that might be a bit overkill, because we've got two checks checking for the same thing, but one will stop the other actually needing to be checked. So what we want to do is, I think we want to actually leave this check in that gives a little bit of information to the user, because otherwise we're actually going to be erroring silently up here. If this doesn't exist, or if this node already exists, then we're actually just not going to do anything. So let's remove this code from our dep node, and let's also remove this code from our DAG node, because we do not want this. Okay, there we go, that's perfect. So we've got our divider. We don't need to copy our string, repr, or equal dunder methods, because those are essentially being passed through the class hierarchy. But let's go ahead and create our nodes, or our node getter and setter. Okay, perfect. Perfect. So these this node property getter and setter returns the current node, and it also sets the new node. It converts it to an mdag path, a special Maya Python class that represents a hierarchical path to an object in a scene, and that, well, if it's valid. Okay, so let's go ahead now. We see we've added one new item which we don't have, which is to mdag path, which is coming from our OpenMaya. So let's go over to OpenMaya, and let's create ourselves another little function. We've already got one usage because we have already put that in, which is awesome, and giving us all that information. Let's now copy everything from above. So let's add a little docstring in as well, because this is going to essentially convert our node into an OpenMaya DAG path. This function will take a node as an input, and it'll convert it into an OpenMaya mPath object. Let me think, anything else I need to say? It internally, I think it uses the toM object function to obtain an OpenMaya object representation of the node, which is giving us all that functionality as we've seen before with full path name. The only difference with this one and the dependency node setup is that this is looking at dependencies. So this will give us, for example, when we do full path name, this will give us this full path when we request it. But okay, let's have a little look at this. So an OpenMaya, I should say DAG path here, and that's actually pretty much the whole string sorted for the explanation. The node is a string, taking a Maya node, so that is also the same. And this will return an object, which is an OpenMaya object. Again, the same. So let's see what we have down here. And again, this isn't actually too bad with the explanation, because this M object does have some similar functionality. But we're also going to put in another example just to show a bit of difference, which is partial path name. So this output will both give us the string. Oh, I'm getting a bit of lag from the recording here. I might have to pause this and continue if you feel a jump. But otherwise, yeah, here you go. We see what's happening. So we've got partial path name, full path name, and these are both spitting out this information. Left-hand joint, and then the full path to left-hand joint in our imagination here, to right here. So now let's start with the actual functionality. Brilliant. So we have written out our new function. Let's go through this line by line. In the first line, we are taking our node and we are converting this into a my API object. And then in the second line, we are essentially, if the object has the function set of type kDag node, then we can get the path node in the DAG. And this is returning an mDag path object, which represents the hierarchical path in the DAG to the node. So it can be really useful for us in DAG or in DAG dependencies, essentially. Okay, perfect. So let's see what we've got up here. Reformat the file. I need an extra space. Perfect. Okay, we'll go ahead and press Control Save. Oh, and when I'm finished writing code, I'm going to put a new logo up, a little pause, and that'll just kind of give you a little bit of a heads up that you can pause, copy the code, and then we'll continue writing. Just because there will be quite a few sections now where the code will actually be bigger than my window, but I don't think I want to make the code smaller because you might not be able to read it so well. So that's just a little heads up there. And now we're going to jump back into our DAG node, and we are going to go straight ahead and start writing in our new section. We're going to, oh, actually, I've just realized we've got a highlight red here. That's because I've done uppercase for node. Absolute special case. Okay, here we go. So let's tab in, press add property, and we're going to create def, and we're actually going to give the public or accessible DAG now. So self underscore DAG with the dot notation. So we've got our class instance, and after we've accessed our class instance, we are then returning the DAG. So we'll keep that section completely cut off from everything else, just so it's its own area. So okay, now let's move on, because essentially this is quite important and you can use it later on, essentially depending on how well you know OpenMire. But this is the property that returns the OpenMire mDAG path associated with the node. So we'll need to access it within our class itself, but it would be but it's also useful to you actually to be able to access yourself if you ever need to in the future. So now let's access it and create our path and our full path accessibility to it. So we're going to have two more property functions. Let's create these. Okay, perfect. So now we have path and full path properties. These properties get the name of the node in the Maya scene, with the path returning the partial path and the full path returning the full path. So obviously very useful if you accidentally did have names with or multiple nodes with the same name, that you actually know, depending on their path, what their full path is, so you can actually differentiate between them. But also in a way that this will be very useful for you, just to make sure that you can get the full path for items, knowing how to jump back and forward depending on their dependency. But okay, that is perfect. Let's add another divider. Obviously, you don't have to add these are just my preference, but yeah, I find them useful. Now let's get another couple useful properties. We're going to get some shape properties now. So we're assuming that now, because we have dependency within our node, that our node will have shapes, or it'll have sub-items below it. So shapes, again, it doesn't have to have just one shape. A mesh item can have multiple shapes, much like a curve or a NURBS curve or any other item. So let's create that functionality now. So you'll see here within shapes, what we are doing is we are using the list relatives Maya commands functionality, and we're using that to essentially return all the shapes, full path of them within our scene. And then we're actually appending those to a list, making them into DAG items so we know their dependency and their full path. And then we're returning that list of shapes to the user. But let's create one more, just imagining that we've only got a singular shape so that we can put that functionality in too. Okay, perfect. So what we're doing here is we are gathering one shape, assuming that there might only be one. And if there is a length of shapes, then we are going to grab that one shape. And if there is no shape, so if the length is 0, remembering that anything above 0 will be anything above 0 within a Boolean response will be true. So if this is false, we will just return that one shape. But if false, sorry, we will return a DAG node none. And this is because it's common convention that when you're working within a class nodal system, you actually return class nodal items. And that is generally a convention that's kept with any items that could be known. So maybe you're getting an attribute which is a string or an integer. Well, that would be fine. You'd leave those as string as integers or integers. But when you're gathering items within a scene and you're using a DAG-based hierarchy, then it's best that you use the DAG-based hierarchy to pass those items back. Just in case you're wondering why this is why I'm always passing back either a DAG node or a dep node or an attribute node, anything that we're working with in the past. Yes, we can just return a string, but it's actually best practice because once we now get this string back, once we've got this back from our call within whatever our script is doing, we can now go, oh, okay, does the shape dot exist? And if it does, great. If it doesn't, then fine, we can move on. But it gives us then a consistent way of actually writing code and interrogating all of the objects that are gathered from our class-based structure. Brilliant. Let's add in our divider again. And now let's move forward. Okay, let's look at another few properties now. Okay, perfect. So what we're doing here is we are, again, accessing a property of our DAG node, and that is called children. And we are then getting a list of all the shapes. And then for each child within the full path of our node, we are going to essentially cycle through that and try and find all of the children. So we've gathered shapes and all of the shapes of our item. We are now going to make sure that every item gathered after this is not within that list. So if child is not in shapes, we're gathering a list back here from list relatives. And we are saying, okay, well, everything gathered from here, we're going to call that child. We're going to cycle through it. We're going to say, well, if that child is not in the list we already have from shapes, then add that to the children list and append adding that again as a DAG node so that each item is a DAG node, and we will return those children. So if we have one group with 5 subgroups and we look at that group's children, we will get all of the children that are just below that, essentially. This is just gathering the children, though. So we'll do one now, though. We'll make another function because we want to also grab the children and the subchildren of an object. So if we have subgroups, we want to grab all of the all descendants, essentially. And that is just AD along with this command here. So we're going to add that new command now. Let's first start by, no, we won't copy. We'll just write this new one out. Perfect. Okay, so we've now got our 2 groups, so our two properties of our DAG node. And what we're looking at here is children, which is just getting all the children of our group. So again, we've got one group, and then we've got 5 groups below it. This will get just those 5 groups. If there are more groups within those subgroups, we're not going to get them here. We're just going to grab the immediate children. Okay? But if we use all children, what we're using is this little flag here, which is saying all descendants. So you can go ahead and check the information within Maya commands by searching Maya Python commands, and you can have a read through all of these arguments to see what they're doing. But what is happening also here, a little bit of Pythonic magic, if we get none back from this call, which again, Maya might do, because there might be no children there, then what we're going to do is actually give ourselves this empty list. Because annoyingly, you'll see this code a little bit and a few times. Annoyingly, what Maya does is provides us a none if nothing's found here, which is fine. But if we want to always make sure we're able to cycle through a list or put it into a loop, what we can do is just go, well, okay, our call, and then if our call doesn't find anything, actually we'll just use this list. Okay, so it's kind of a this or this, and it'll essentially use whichever item whichever item either comes last or has a value. So if this came back with a list, then it's a list with value, so it would override the need to use this empty list. So we now have these, but now we need to try and gather or access a way of getting the information for our parents or all parents. So let's write those out now. Let's do the exact same thing as we've got here. Okay, perfect. So we've got our two new properties here, and what we're doing is we're using now the parent little flag. So within list relatives, we are going to gather the parent item of whichever node that we are in, and then make sure that from this list we gather the first. That is if there is a parent to it. Obviously, this could be a dep node, which has been passed through the DAG node functionality. And so in that case, you would then say, well, there's no parent, so we wouldn't return anything, which we can return none, I suppose. But at the minute, we will quite literally just not return anything, and let that be, we'll let the functionality kind of be sorted on the other side of this script within the module that's using this property. So, okay, now the more interesting bit, so we've got all parents, but we're doing something interesting in all parents. We're actually cycling through every parent item with a loop, and that is until parent equals nothing. So until we get nothing back, okay, we are going to keep on cycling through to find all the parents. So this will give us the list of all the parents, because we've got our parents empty list here. We're then appending to those parents that the parent that we've just found, and then we're going to say, actually, well, okay, parent. Let's look at that parent's parent, okay, because we've got our new self, which is essentially this is our new item, and then we are saying, actually, well, this new item. Let's find that one's parent. Let's add another little divider and space there for PEP conventions. And now let's write another couple of functions. So what we have here, we have our order and reorder functions. These are related to the ordering of the nodes and their children. So if we have a subgroup, if we have a group with 5 subgroups, again, this will allow you to reorder those subgroups depending on their index. So you can either get the current position of an item. So if it's number 1 out of those groups from the top to the bottom, then you would get that index back. So we're actually saying, well, okay, let's get self.parent, let's access the parent item. We're then going, because we're being passed back a node, again, like we said, there's very useful functionality. We're going to then access that parent's children, which is essentially the group that we are in, and then get our index using a Pythonic way of just index and self. So we're then getting our own position within that subgroup. And this might feel a bit confusing, but just try and think in your head of and follow the chain of what we're doing. We've got our own item. We're then grabbing its parent. The parent is giving us back another DAG node. So again, we've essentially just started again with that parent node being a DAG item. We are then requesting to get its children, which will then give us a list of all of those children, which are all again DAG items. And then we will index and find ourselves within that list. And then we can use that information if we need to in the future, reorder items based on maybe alphabetical order or consistency of the order of which item you would like at the front. We can then use our reorder functionality here to actually reorder them. Again, if we just type in the reorder Python Maya into Google, this is what we get up. We get the information with, okay, well, relative to other siblings, you can either use front or back, so you can also add more functionality for this. You could add maybe reorder to front, reorder to back, and then every time you add a new item, you'll know exactly where it's going, or you can put exactly where it needs to be. But let's add another divider, and we'll continue. So we're now going to add some more ability to parent to world and move our items around. But let's just sort out our parenting at the minute. So let's add some new functionality here. Okay, perfect. So we've got our parent to and parent to world functionality. So as we can see here, the parent to will allow us to select our own DAG item and then parent it to another. So we've got self.full path, so we're accessing our own item, and then we're going to parent it to any item that is passed. But also we want to be able to parent a world. So we're just going to give ourselves the default functionality, which is parent to world. Okay, we won't put this as a property. I know it's not taking any information, but obviously this isn't actually returning us anything. It's not a property. This is still a function. So therefore, when it's called, you should still have to put, say, your object parent to world, and then open up the parentheses, because this is a function that is being run upon your object. All right, let's create a few more bits of functionality here. Let's do some moving around. So let's say we want to move our objects or match their positioning to another. Okay, so we'll create this function in a second. We'll call match move, but let's again keep with this kind of move to parent to functionality naming that we've gone here, and let's imagine that we want to move our item to another that we've got in our scene that we need to do. What we want to do is be able to have those items in the code and just say, yeah, move to, and then provide the name where we would like to move our item to. So again, we're not doing any parent constraints, anything else that we are having to kind of do, which is putting that all into one line here, which again will be in our match move function, which we haven't created yet, but we'll go and create in a minute. And then let's say we want to do this the other way around. Let's say we want to actually move a whole group of items towards this item itself. What we can do is just change that to plural. We can actually put this as move here. And then what we're going to do is change that to being plural. And then we are just going to switch these arguments around a little bit, because now the driver, we go for a driver-driven mentality. We've got self.full path. And then what we're going to do is we're going to then add this list of items that we actually want to move over. So what we're going to do, actually we'll keep that as a list, because we're going to make this all work as a list. And we are then going to cycle through our list of items. So again, we're kind of treating these items that they might actually be DAG objects. Obviously, if they're strings, we're going to pass them through, but we actually want this functionality to be able to work without DAG items. So we're going to make sure that everything that we pass through is actually a string. So we're passing through the string of the object that we have at the moment. We're going to pass through the string of the item that we're moving to. So we're going to make sure if it isn't a DAG node, it won't hurt to encapsulate anymore, because once it's passed through, it will use the dunder method string to actually get the string. And so we'll just be reinitiating it really. And then we will make it into a string again as our name. Kind of a little quick check just to make sure that we have the string from this item, because we are working in a system that might be dealing with or without DAG nodes. You don't have to be, but we might as well just take care of them at the same time. But so in that same methodology, let's type in here DAG node, open parentheses I, and then for I in items. So we're using a little string comprehension here to make sure that each one of the items passed through is a DAG, and then we're going to do dot name. Perfect. Okay, now let's create this match move functionality. Let's put this in a common, I'd say this is a pretty common function. So let's go for within modules, within the base folder of modules, we're going to go for Python file and common. Any functionality that you think, actually, this is a pretty common function, we're going to put it right at the base level. Okay, perfect. And now let's write ourselves a little doc. Let's copy over our docs from here. And we will just say that this will deal with all common needed functions. Or functions. Feels like I did a real thing, function. All right, and what we're going to need in here is we're going to need to import Maya commands. Let's sort out our inputs. Okay, perfect. So we've got our match move. Let's put a pass in here, and then we can go ahead and import it. Okay, perfect. 3 usages already. Amazing. Okay, let's reformat the file. Now let's copy a doc string as well. Make sure we have a doc string nice and clearly written out for us. Okay, perfect. So we've got our doc string here, which is going to kind of how we envisage this running. And we're now going to kind of work back to this doc string. So we're going to take a driver location object and a list of driven items to move in that order. The default option is to use a parent constraint to move both the translate and rotate unless the point or orient attributes up here are set to true. The selection it takes is a list. These are the list of the items in the scene. With a driver-driven mentality, it means the first item within the list is going to always then be the driver of the position of the other items. Okay, so that is what we set into place up within our DAG node. You see, the item we are moving to is the item that is passed. This is our driver. And then we are moving our object here to this item. So we're moving to this item, the driver. And then move here is assuming that we want to move a bunch of objects to ourselves. So we are ourselves, the object, the driver, and then we are getting the list, adding the lists together of all of the sub items and making sure that we have the string names. Perfect. Okay, so there we go. Now let's go ahead and write the functionality for this. Perfect. Okay, so here is our match move item. Now we can use snap or some other kind of options within Maya, but let's keep it simple anyway for the moment. We've got our parent object, which is within our selection that is being passed the first item, so the indexed first item, which we are popping out of that list, and we are going to save it to the parent object item. The rest of selection will remain unchanged. So if we have 4 items, or let's say we just use this example that we have here, we have sphere geo, and we're going to move model group over to it. So we've got our driver. We are essentially popping this out of the list and putting that as the parent object. And then we are going to cycle through the rest of the list, and we are going to try and go through our options. So if point is true, which it's not, and orient is not, if either of these points are true, then these will be set. And if they're not, then we will just go straight through and we will go for a parent constraint if neither of those are set. And essentially what happens afterwards is we will then delete the constraint. Or do we have maintain offset is set to off within all of these. So if we move to if we do a parent constraint, we are taking the translate and the orient and the rotate, and we are making sure that those are both set here and that the item is moved over. Now, one thing we are doing here with our try except catch is we're actually going to inform the user if something doesn't move over, but we're not going to stop the script because, you know, there may be a reason for something being locked off in a scene. So maybe we don't want that to stop the whole script. But what we are going to do is we are going to tell them the name of the script. We're going to say there's been an error here. And we are then going to print out the error. So we've got this really cool line here, which is exception as e. We're storing the exception as the variable e. And then what we are doing is we are getting the type of error. So we're actually, because this is a class, we're getting the error type. We're getting the name of that. And then we're actually going to print out what the error was anyway in plain English, which we'll look at in a little bit. But here's our function for match move. So that gives us that ability. Now if we go back to DAG node, you'll see that everything is now not red because we have our match move functionality. Perfect. Now let's add another property and another bit of functionality that will be really useful for us. So what we're doing with this property here essentially is we're just going to actually return the parent, because another common phraseology is offset. And what we want to do generally is create offsets, or this is kind of how I was trained anyway, or how I was taught, is that we have offsets for items. So we might want to actually say get an offset. So we can do our object. We can actually go, we can either go parent and just get the parent item, or we can actually just get the offset, the item. And now what we're going to do is we're also actually going to create an offset. So we're going to have the parameter in this. So we can actually also then go, so object, and we want to be able to create offsets. So if we need to, then we can just create an off path, which will by default create an offset group, move it to the position of wherever our DAG item is, and then it will parent our item below that. Again, giving us that ability to, within the scene, kind of have a zeroed out controller or a zeroed out piece of geometry or something that's been moved in the scene, but you want to actually zero it out, but while maintaining its attribute values. Okay, so let's create that functionality now. Okay, perfect. So what we have here is our create offset functionality. Now, as default, this will just create you one subgroup, but it might be nice, in certain circumstances to be able to create multiple offsets if we need them. We might want 2 or 3 because we're going to be adding some other items to the below subgroups. But what we can do is just set a default for it to be count with our keyword argument here. Now, if self exists, again, we can't really use this functionality unless this DAG item exists. So if self exists, then we will go through our looping through this as many times as we have within our count, and then we will create an offset, and we will again return the DAG node of that offset item. But we don't have an offset item or a create offset functionality yet. So let's go ahead and create that somewhere. I'd say we probably do it again within our common functionality. So let's add that up here. Okay, perfect. So we've got our docstring, and we now need to just populate some of our arguments. We'll have selection, and we will also have group name. Of course, we could also just turn off caps lock. So this takes the selection passed in the scene or the selection passed and creates the offset groups in their locations. That's not the right terminology. And the args it takes our selection, which are a list, the group name, which is a string, which again you can change. And this returns a list of the off groups that have been created. So an example, create off group for the sphere geo, and this will again give us the off group naming. Perfect. Yeah, okay. I think that's everything we need. Now let's go ahead and start writing out that functionality. Okay, perfect. I will just put a little pause on the screen here so you can catch up and write up with this code. But what we are doing here is we have got our group name or our newly created groups, okay, which we will add all of our newly created groups to. We've got our offset group names, which I've just given us some default names that we can run with here. So we've got place a group after the default, which is off group. We've got place off group, sub off group, zero off group, base off group. Again, just a very simple way of us kind of cycling through a list of names that we can use within this function. And now we are going to iterate through our selection, and we are going to make sure that we essentially have the number for the output. Again, more for printing out if you have an error. Yeah, but then we are going to go through and we're going to say if the item does not exist, we're going to print off that information, but we are not going to stop or raise an error to stop the script. And then we are going to essentially give ourselves a few bits of useful information which aren't being used yet. We're going to get the off group parent, and we are then going to cycle through the list. And if the current item ends with the group name, we first remove that name from the offset group names list, and then we also want to remove the group name from the current item name. And if it doesn't end with the group name, then we keep the name as is. Cool. So if you can just copy this code down now, and we'll quickly get moving on in a second. Perfect. Okay. So here is the end of the function. So we're starting off, we've got our first section that we've just written. And now we've got the last section. And here, the group name, we are going to create a new group name by appending the first available name from the names list. So what we're doing is we're using this iterator to grab the next available item. And if there isn't a next available item, we are returning none. Okay, if the group name was successfully created, then we create the new group. So we go through, because we have a group name which isn't none, and we then create our group, which is initially empty, create it to world with the group name and the prefix and the suffix that we've added to it. Then we're then going to use the match move functionality we've already created, and we are then going to move that item, move the off group to the position of our item. And then we're going to parent our item to that off group. Next, we are going to essentially go through and we are going to say, well, if the off group parent is not the same as the string item, then M parent the off group to the off group parent. So we essentially are going to add our group to the parent positioning of the item that we just created. Oh, sorry, of the item that we have just added a subgroup for. That's what pickwalk does. Pickwalk essentially takes the item you pass and it walks up from that item. So if you have two groups, group A and group B is located below group A. If you pickwalk from subgroup B, it will give you subgroup A. And then we are returning those newly created groups. Okay, brilliant. So we've got our two common functions now. This is a bit of a workhorse kind of function. It'll get used a huge amount when you're going through your scene, because you always want to create an off group to zero out items nice and cleanly. But you also want to have them named consistently and nicely. And that's where sometimes having a list, you'll always then have consistently named subgroups. Perfect. Okay, let's go back to DAG node. Jump down. You can see now that create offset is no longer highlighted red, which is perfect. This is highlighted orange, add global statement. No, we don't need to do that because we are returning this item essentially once it has run through. We are going to return the last item. So if we do create 7 subgroups, what we're going to do is we're going to return the last offset name. And what this is saying is, well, why don't you create a global item, say here, for example, that says none. And you see it's no longer highlighted orange. Annoyingly, obviously, that's just where the ID is not perfect. We don't actually just need to do that. It's just, it might increase readability, but it also just increases overhead, and there's no point for such a small amount of code. Okay, let's add ourselves another divider. And now let's add another function. Perfect. So again, a function to be used internally by our class. It's called getConstraint, and it takes a constraint type. And what it's doing is using the myCommands list connection to get the constraint type that we have passed through to it. So let's go ahead. We're going to essentially add the ability to be able to parent constrain, geometry constrain, scale constrain from our node to any item, and then also give us some nice functionality to help us automate the what we need to do below that. So let's start off here. So now let's move on and let's do some creating. Let's get constraints. So let's use this method now and actually use this to get all of the constraints that we might be able to use. We'll probably be able to copy quite a lot of the functionality that we now write. Perfect. So what we have here is our get geometry constraint. So if we have a geometry constraint on our node, we can essentially just say get geometry constraint, and this is properly, it will just return it to us. Unfortunately, because we want to also use geometry constraint or parent constraint as commands, we can't then also use them as properties. Just because of the way that Maya works, it doesn't have a full understanding of the way that Python works. So that is where there's a slight kind of disparity between how the code is written, but it's so small, it's kind of insignificant. And now what we need to do is essentially just copy this and then copy it down for aim, orient, point, and parent. I think that's everything. So, okay, let's start with, so we've got aim. Let's have a look. Let's do the first one with aim. Now, so each one of these items will cycle through and then return back the parent, the point, the orient, the aim constraint for us. And now let's have a little look at getting the constraint weighting attributes, which again are really useful for us, just to be able to key to, or be able to set driven key, or be able to control essentially with how much strength each item has. If we have parent constraints, say a locator between 4 points, we might want to be able to set the strength of each one of those points. The main problem with the Maya parent constraint within Python, the Maya commands doesn't actually list out all of the connections very easily for us, or very nicely. So what we're going to do is we're actually going to list those out ourselves by getting the constraint. So getting the constraint that we want to get the connections from. And then what we're going to do is we're going to use the Maya constraints list atter, list all the attributes of our constraint, and then any that have a W within them, we will then say, well, if that W is within the last but one item, or the last, or in the third back item, then we are going to use those because they will probably have the weighting attribute information on it. And that'll be very useful for us. So let's have a quick example in Maya. Perfect. Okay, so let's open up our scene, and we've imported our DAG node. We're importing Maya commands as M, and we're going to create a polysphere here with the name sphere geo. And that's worked. We're lucky. We've got enough functionality for this all to work at the moment. And let's now, actually, let's duplicate our sphere a few times. Now let's say we select all these items and then our sphere geo. We're now going to select the rigging window options, and then we are going to go constrain and parent constraint. So see what we've got is this parent constraint with all of these target items here. And what we annoyingly can't do easily within Maya is get those listed out for us in a very usable way. But what we're going to use is our functionality to essentially help that. So let's jump back to our window, go to our DAG node path, copy the constraint weighting attributes variable, then open up our Maya again, see if this works for us. Now we can do even get the constraint, but what we are going to do is just say parent constraint. And perfect, look at what it gives us. So it is cycled through and it's given us each one of these attributes that we now know we can turn up or down. So each one of these that we can turn up or down. I don't even have the window open. Let's go to panels, save panels, and script editor perspective. There we go. So if there were, let's see, got that. So we've got our sphere. But now, which item is this? I moved number 2. So if we turn down 2, see, it'll turn off the influence of it. Or we can turn it up, which again, this is all really useful to be able to do. But we need those attributes to do it first. And we're going to change this a little bit when we have our attribute class to make it even more readable. But at the minute, that's everything that we need for there. So that's a pretty cool little bit of functionality for us. Again, just gives us a very easy and readable way of saying, okay, well, what are we doing here? What are we getting? And how do we get them? And how do we list them out in also a very easy and readable way? Which at the minute, I know that what we said was we would return DAG objects. But because this object essentially is an attr, our DAG path at the minute can't take into account attributes because we haven't built that class yet. We're going to build that in the next series of lectures. But what we can do at the minute is just return the string, and then later on we'll come back to it when we have our attribute class. Okay, great. Now let's go up. We are going to copy each one of these the get items for our constraints, and we're going to copy. Move our cursor down and then press Control V. We are going to highlight property and then press Alt and J, and you see highlight each sequential property. And just press delete until they come back. Now remove the delete, and then we're going to press Shift and left arrow key, and then we are going to press Control, Shift, and U, which will make these all lowercase, which does seem a strange choice of commands from the team, because I would say that Control, Shift, and U would probably mean upper, but you know, each to their own. I think it just changes it each way as well, so it can go up and down, which is fine. But maybe there'd be a better key for this, maybe a C, but you know, that's I suppose used in copy, but that would be more of a maybe I'd see that as a case key, but first world problems here. Okay, great. So we've got all of our functions here. And now what we want to do, again, let's go Alt and J, get each one of these functions. I want to jump to the end, and after the self, we want to do comma. We want to now be able to get all the args, because we're going to be using my functionality here, and we're going to be able to pass through any arguments or any keyword arguments that the user passes, but we don't want to, again, hinder what they can do. We just want to actually make it so that we're kind of in-housing the Maya functionality into our class. So what we're doing here is we are going to, again, once we've created the constraint, what we're going to do is we are going to return it as a DAG item. So we're going to go DAG. Right, we're going to go DAG underscore node. Open parentheses. We are then going to go M. I'm going to go open. We're going to put some parentheses in there just to stop that crazy highlighting. Now we're going to go self.fullPath. And then we are going to, after our full path, pass the args. So again, star args, and then star key args. Let me have a think. So what we got there, we've got our node. We don't have the double closure that we need, so that's why we're getting that red line. But we also need to get the parent constraint node, because I think we returned a list essentially by any constraint, any of the Maya commands constraints. So we're also going to go get the first item in the index of the list that we create. And now what we've got is our way to constrain any item that we need to within Maya from our node. Perfect. Now let's add a little divider. Let's actually add one more just to make life a little bit easier. We're going to add one which doesn't exist, but just because it's something that you will do most of the time. So we're going to add parent, scale, constraint, because you will be doing this quite a lot of the time. Let's say we just pass the parent back. Actually, let's just do that. But what we can do is just make sure we also do create the M scale constraint, which we don't need to create as a DAG node because, oh, now I'm jumping across the screen, because we are, I'm just going to essentially use it and then throw it away. But if we do need something passed back, we can do that. And you can always update this in the future if you need. But I do find this quite useful actually, because a lot of the time when you do need a constraint, you'll probably also need a parent constraint. So it just gives you that functionality if you need so. Great. Okay. Wow. We haven't done a divide in a long time. This has all been constraint useful information or constraint functionality. So we'll, yeah, I think that sounds about right. But now let's move on. So now we're going to go on to color functionality of our DAG node. So if we have a dependent item with color, then we're going to be able to set that color. Perfect. Okay, so what we've got with this first property is just getting the color. So if we have a DAG item with a color, or if it's sub shapes have color, what we want to be able to do is find out what those colors are. So we're going to be able to just say object dot color, and then we'll get that color returned back to us. But what we also want is, and which will return an int, because the default in Maya is when you request a color, that it will return an int. But we also want to be able to return that as a string. And we also want to be able to set the color. So let's add those two functionalities now. And now I'd like to be able to set this as a getter and a setter, but you can't do that within, there's essentially the functionality doesn't allow for looping. So we'd have to do, to set the color, we'd have to do an equals, which we don't really want to do. We want to be able to open brackets and set the color, so we can do it within loops, we can do it within list comprehensions. We don't want to lock off that functionality to be so limited. So we're going to set that as its own function, essentially. But let's create the functionality that we need, the other property that we need, actually. Perfect. So now we are going to use our color, the integer that we are returned if there is a color, and then we are going to be able to say, get the color from that integer. Or so we should be able to say get string from that integer, but we probably should actually state color within that functionality within this module. Otherwise, it might be confusing if get string from integer. That might not read well if we just import that module by itself. So we'll just say get color from integer. Perfect. Okay, now let's add our set color functionality. Okay, perfect. Perfect. So we have our three new functions here, two properties, one function. So we're going to set the color with this one, with our color module, which we haven't made yet, and we are going to be able to get the color and set and get the color as an int from an integer with this one. So let's go ahead and make these. Let's go ahead from above and let's go from utils. I'll add that to utils. Actually, this should be in utils. So let's open up our window within utils. Let's go new Python file, call this color. Now let's steal a docstring. Okay, perfect. So what we have here is our new color module, or new color module. And we're going to add three functions in here, which we've already stated within our DAG node. Actually, let's put it over here within our DAG node. And these are get color from integer, and set color. But what we need to do is, if we're going to get color, if we're going to change it from an int to being then a string, what we need to do is have a color dictionary. So we're also going to need one more color dictionary. And we're going to store that within common names. We'll put that. So we're going to put that within control modules, control, and then common names. Because I'd say, actually, no, we won't put this in control. We'll keep this in utils. within common names, because obviously it won't be just within controls that use that. Joints can also be a different color. You can set a few items locators, some others. But let's add this to common names now. So within utils, let's go new Python file and common names. And again, we will just pop over and add a new dictionary. Okay, so we have our color dictionaries, and you see we have our integers with different namings that we can use. I've put underscores in them, but you probably could make quite easily make a sanitized script which just remove the underscore. So as you're searching through, you could either search with or without the underscores. So see from Apple all the way down to purple, 31. These are the default colors that come with Maya. I believe that RGB colors were added from, I don't know, 2019, maybe 2020. But these are the default, which I use for back compatibility in case I go to a company which is still using Maya 2016, for example. Okay, great. Let's jump back to color. Now let's write our first function. Okay, perfect. So we have our get color from integer function, which we need to create. Let's copy over the other two items that we need as well. We've got get color from integer. We've also got get color from string, or get color, set color. So let's copy these over. And now what we're doing is with our color dictionary, we are taking a string of color and returning Maya's number or index setting for the NURBS color, essentially for the NURBS color. And we'll just say that, actually it's a bit easier to read. So it takes a color, which is the int representation of that from the index of Maya's indexing. And we are then going to return the color from that. So we're going to use the integer to grab the number. And what we're going to do is cycle through our dictionary. And we are going to say, well, let's find that item. So if the color dictionary I equals color, then we will return it. And if we don't, we'll actually return an error anyway. So it's kind of perfect that we say, well, we can't find that, but we'll be able to find that anyway. So get color from integer, 24. And the output will be the string dark orange. Perfect. Now let's do one for get color from string as well. I think we're going to be needing that as well. So let's do the exact same thing, but with get color from string. Perfect. Okay, so what we're doing here is essentially the same thing. We are taking a string of a string representation of our color, which we are assuming is going to be found in here. Again, I've done a bit of a lazy method here. I've kind of put underscores. I've done both representations of most items. But what I would say is you'd probably be just easier just to just to take out all the items with an underscore and then just do a string appendation on the passed item through. So if any underscores are found, then you just change that and then you put in the item, which we can do pretty quickly. But so to do all that, let's say take out everything with an underscore. Let's find everything here. I think that's everything. Oh no, we got one more there. Perfect. Okay, that is all of the items. And now we'll press, go back to the line, Fn, and then Control, and then we'll press Shift Fn and the end of the line, which will then just delete all the items, then press backspace. You see we've shortened our dictionary up quite quickly already. Put these in groups of 3, that might make life a little bit easier. There we go, perfect. Okay, so we've shortened our list. Okay, that's one nice way of looking at it. And now if we go back, what we can do is, along with our string lower, what we can also do, so this one's using int, so we don't need to worry about that, but with this one, we can now go dot, we can also go dot replace, and if any underscores are found, we just replace them with a space. Okay, great. Now let's create our get color functionality. Perfect. So here we have well, the get color functionality, which gets the color of an object shape passed. This will search through all of the shapes, and it will essentially pass back the color when found. This is going to take a string, and it will return the integer of the color index found within the color override, the default kind of Maya coloring system. It returns an integer, which is the default that Maya returns. So if we do get color with hand control, it will pass us 26. And what we're doing is we are initially listing the object relatives. So we are gathering all the shapes from that item, which is either going to return us a string or none, or sorry, a list or none. And if it doesn't return us a list and returns us none, we just do an empty list. And then we append with the item that we already have. Now, we want to check that the item we already have is one of these types. And then from those, with all the types that we have left over, we will cycle through them. And we will make sure that we get the color override information that is passed back to us. Okay, and that is if the color override is enabled. We don't want to bother with anything that's not enabled because it won't be colored or won't be changed. So perfect. All right, now let's do let's do our set. Let's do our setter, which is a little bit longer, but we will do our set color now. Okay. Okay, perfect. Okay, so we have our set color here, and this takes a list of objects and sets their colors. The args it takes are objects, which is a list of items to set the color of, and a color, so which is an integer or a string. So we can change that within the function if we need to. So for example, you just say set color 24, and the output is that the color is essentially changed, which we can do. So we'll just say this actually output. Perfect. Okay. And here is all the functionality. Very sorry, it fits just perfectly in the window. So you can see we've got our doc string, and then right below that, we are now doing our first check, which is if not color. Actually, I should say probably pause now, copy out the code if you'd like, and then we'll explain it through after you've written it all out. But we're first checking that if color is not passed, and if that is left as none, then please, we are going to inform the user and say, please pass either the color number or name as well, doing our percent get, but we'll or percent string appendation, where we can always obviously just do the format if you would need to as well. But okay, so we've informed the user if that is not true, and now we're going to use 6 and 6 string types provides us with a tuple of string types that are valid within Python 2 and 3, and it's a nice way of essentially checking for the is instance color of types, because within Python 2, within string types, you have Unicode. But within Python 3, you only have, I think Unicode is default, so you don't have to worry about that. So this is a good way of checking for everything that you essentially will need. And then it will use color and get color from string. So we'll pass it the color if color is a string. So we'll get the integer that we need. And then it will basically say, well, if it is not a string, and if it's not an int, well, then it's going to raise another error. Format not understood. Please pass a color number or name. So again, it won't happen too often because you'll be quite used to the colors that you need to use. And again, I only ever use this with the string because it's so easy. I just put in red, blue, light blue, red, pink. I mean, it makes life very easy for what I'm using, or yellow, green, brown. I mean, it's great. Okay, and then we're going to force the objects to be a list. So if we have a singular object, we're going to say, well, if, again, another way of just saying is instance, if the type objects passed is a list, then fine, we'll leave it as a list. But if not, make it into a list, please. And now we're going to extend the objects with the shapes and filter by the selection type. So we're going to say again, we're going to get all of the shapes, and if there's none, we'll just continue on with our list. And then we are going to extend that selection with the long names of those items, or with the items that we already have. And then we're going to add to this extended list the shapes that we've just gathered. and then filter them down by the items that we want to set. Okay, now we're going to actually go through and override all the colors. So for object in objects, for all the objects that we've gathered, we're going to cycle through them, and we're going to, again, override the color. So if the item has override enabled, which is 1, because we are doing, we're doing if object exists, so if this exists, and if the object's color override exists, which again, they kind of work together, so they probably always will be there together. But we are then going to say format the object name into there, and then color override, and set that to 1. We're going to allow the overriding of the color of that object. And then we're going to set it to the color integer, which we have found up here, which is either passed directly as an int or as a color. Great. Let's get back to DAG node, and then let's move on from the color settings. Let's create the last bit of functionality for this class. Oh, this video is nearly 3 hours long. That is, I'm going to have to edit this down. I might, if I can edit this down enough, I'll keep it as 1 video, but I might have to do this as 2 videos. So we'll see where we are. I've just realized how far this has gone. But okay, we've got all of our color set up now, which is giving us quite a nice bit of functionality. Let's do a little bit now with the showing and the hiding of our node. So we want to be able to set the visibility and do that nice and easily with maybe just 1 word. But let's start off with our first function here. Okay, we've got our first function. Essentially, very simply, we're going to, as we've said, use some methods to change the visibility of our nodes, either set them to visible 1 or not visible 0. And to do that, we access the attribute v, which again, when we have set up our attribute section, we'll be able to call this a little bit more Pythonically. But for the moment, we are going to use Maya commands, the setatter Maya command, and then we are going to insert our item and then use that with the v. And we're going to use the full path just to make sure we've got the correct item, and then set it to being the value that we pass. Now let's set up even some more shorthand for this. So let's go with show and hide. Okay, and we will copy over our divider. Oh, badly. Come on. Okay, we're not going to indent, fair enough. But okay, so it simply does what it says on the tin. So we can now do our object, dot notation, show and hide. And that will automatically use our set visibility function to do as we need. And these, again, these are functions. These are running functionality without gaining or returning anything. So these aren't properties. But yeah, again, they give us a nice short way, just 4 characters, and then we've got show or hide, which is quite nice and easy for us as we go through everything. Okay, last thing, let's make sure that we can gather and delete the history of our node, and then also duplicate it, and I think we're good. So let's start off with getting our history. Okay, perfect. So we have our history function here, which essentially gives us a history variable, which we are then cycling through all of the history. We're using list history, Maya commands, using just essentially the full path of our item. And for every node that is found within the history, we are going to create that and move it and create a DAG node from it, so that when we're returning it, we essentially can work with any of the items in a Pythonic way as needed. But if self exists, again, we should probably, there's one thing we're doing here. We're checking if self exists to see if there is a history, but I'd probably might just do that before. So what we can do, just go if self exists. We'll do this. We'll remove this from here, and then we can just return, if not, return an empty list. So that kind of feels, again, a little bit more of a nice hierarchy, but it also, again, saves us running any functionality, saves us bothering to even call the Maya commands if the object doesn't exist that we're working with. Perfect. Okay, now let's delete history. Okay, perfect. So we have got our delete history. And again, if the item exists, we are going to delete from the full path the construction history, I believe that stands for. Let me just find that item, open that up. And here we are. Okay, perfect. Construction history, yes. Remove the construction history on the object specified. Yeah, so let's say you've got a sphere, you've subdivided, you've removed edges, and you've extruded, you've done some extra bits. From this, you can literally now just go channel box, delete all of that history. You don't want all those nodes going through when you start rigging that item. Okay, now let's duplicate. Now we want to again have this in a nice Pythonic way. Perfect. Okay, so what we've got here is our duplicate node. Essentially, any node that we have, we can duplicate it, and we will be using the default Maya commands duplicate. But what we will be doing is just, again, using it straight from our node, and then we can use all the keywords that are needed. So for example, n, we can duplicate with children, without children. Again, all you have to do is search for the duplicate Maya commands, and you can see all of the allowed commands with that. The value error. Okay, again, if this doesn't exist, we probably want to inform the user here, whereas in any of these other items, maybe we don't care. Yeah, but if we try to duplicate something, it might be useful to let the user know that you're actually not duplicating something. But let's also do 3 arrows just to signify this is from the rigging code. Okay, perfect. All right, so I think we've gone through everything now, more or less here. I think that's everything we need before we go into our test class and make sure that this is all working. So we've done, yeah, quite a few lines of code here. Again, obviously this is just a base, essentially. You can add more as you need going through. We'll try to talk about how you do that as we add a few more setups. But this is one of the fundamental building blocks of all of the rest of the hierarchy that we're going to be building. Next, we're going to focus on the attribute setup, which again is kind of hand in hand with how powerful the system is. It only becomes powerful if we can also access Maya's attributes in a Pythonic way and be able to append them, update them, rename them in the exact same way that we can Python nodes. If we can't then access the attributes, it's kind of it kind of gives us feels like maybe a one-legged approach at this. We want to have we want to be able to take a full approach to having a Pythonic setup in Maya and abstracting all the difficulties from within Maya to one system that we can use, and then make sure everything conforms to a nice strict convention of coding practices. The one thing that I do that does stress, I think, a lot of developers out with Maya and with Maya commands is that the conventions aren't consistent in a lot of the time. Like I said, with a lot of items, you'll receive, when you create a node, you'll maybe receive a list back. Some you'll receive the string, some you'll receive none if nothing is created, but some you'll receive maybe an empty list. There are a lot of times where Maya weren't really consistent with their own naming conventions. And obviously with such a big industry that kind of works off the back of this, it then makes issues for them. But that's where, again, you can abstract all of those issues away by just making your own Python setup. So although it gives you overhead, it does remove difficulties in some areas, and it means that you can increase consistencies, which is always good. But anyway, thank you so much for listening, and we will be heading on within our next lesson into the testing of these classes and these modules, which again will not be quick. But if we have to cut it into a few videos, I'll try and do that. I'll make sure I edit it down as much as possible. Thank you so much for listening. Bye.